Okay, we are on 5.1, identifying acids and bases. Let's take a look at the warm-up. It says a student tested a number of unknown solutions and recorded the following observations. Based on each observation, place a check mark in the corresponding column that identifies the unknown solution as containing an acid, a base, or either one. First one, it turns phenolphthalein pink. Yeah, remember when you added phenolphthalein drops to an acidic solution, it was just clear, right? There was no color. But then as you were adding sodium hydroxide to it, when you guys were titrating it in the fall, it suddenly turned faint pink, and then it turns hot pink. Okay, so that's what happens when you become slightly basic. Feels slippery. Base. Has a pH of 5. Acid. Tastes sour. Conducts electricity. Both. Yeah, because both of them have freely moving ions. Strong acids and strong bases are 100% ionized and soluted. Reacts with metal to produce a gas.
Acid.
Acid. Okay, now we're going to talk about two different definitions of acids and bases today. The first one is the Arrhenius theory, or the Arrhenius definition of acids and bases. What this says is acids release hydrogen ions in solution, and bases release hydroxide ions. Okay? And we're going to take a look at acid-base neutralization reactions, which we talked about in the fall when we discussed double replacement reactions, because these neutralization reactions are a special type of double replacement reaction, which we haven't done in a very long time. It's when you have an acid combining with a base to produce a salt and water. Now remember, a salt is an ionic compound. Ionic compounds are attractions between a cation and an anion. Okay, the cation will always be listed first and the anion will always be listed second. Okay? Okay, so let's take a look at some practice problems over here. Let's classify the following as an Arrhenius acid, base, salt, or molecular compound. A, H2SO4, acid. How about XEF6? Molecular compound, good, because those are both nonmetals. C, base. What's that right there? Does that look familiar? It's acid. That's the acetate ion rearranged. So this is acetic acid. This would be an Arrhenius acid. How about D? Salt. That's an ionic compound. It's a cation, a sodium ion, and the acetate ion, which is your anion. KOH, base. NH3. Okay, this is where the Arrhenius definition for bases is kind of limiting. NH3 is actually a weak base, and that's because when I put this into water, this is ammonia, by the way. When I put this into water, it's going to form ammonium hydroxide. Okay, so this is technically a base. This is going to lead me to sort of give you a different definition for acids and bases that's broader. Okay, it's the Bronsted-Lowry definition that we'll talk about in a second. Okay, now, since it's been a while, we should probably practice some of these neutralization equations, okay? So do you want me to do one and then you guys can do one?
Sure.
Okay. So for the first one, remember there were a couple of different ways that I taught you how to do this. You could either look at the ions, like here we have a acetate ion with a hydrogen ion, and then a lithium ion with a hydroxide ion. And remember the cations in each compound switch. So here we would get lithium acetate. I'm going to rewrite acetate as C2H3O2. I just think it looks better. And then we're going to have hydrogen combining with hydroxide. So this would be my acid and my base making a salt and water. Okay? If you don't like doing it that way, you could also do it by writing it out in words. Remember, we wouldn't want to write this as acetic acid. You would want to write this as hydrogen acetate followed by lithium hydroxide the hydrogen and the lithium switch places because those are both my cations. I will form lithium acetate and hydrogen hydroxide. It doesn't matter to me if you write water as HOH or H2O. They're the same thing. But the only reason I would recommend you do it in words and then convert the words to formulas is so that you don't mess up on the subscripts. Okay? Because a lot of times people look back here and they assume that whatever subscripts you will have those identical subscripts over here. Okay? Okay, why don't you take a look at B and write out the neutralization equation for that, and then we will go over it.
Calcium iodide and water, but you have to like balance it with CaI2. Calcium is a charge of 2. So you need to add 2 before try and then 2 with water.
Okay, so I got 2HI plus CaOH2 produces CaI2 because I cross charges to get calcium iodide, right? And then 2HOH. And you could write this as 2H2O, that's fine. So could you all do this on a test? Yeah? Okay. Let's go on to one more practice problem and then let's make this smaller. Okay, in number 3, they've given us some salts, and from those salts, which are made of a cation followed by an anion, I'm going to predict what the parent acid and the parent base were. What that means is, if I'm looking for the parent acid, I'm going to add a hydrogen ion to the anion in the salt. The anion is the second ion in each formula. So if this is NO2, and I put a hydrogen ion with NO2 negative 1, what would I get? HNO2, because won't these cancel? And then if I put hydrogen with chlorine or chloride ion, what would I get?
HCl.
HCl, because those will cancel. And then if you look on the bottom left of your periodic table, you're going to see C2O4 -2. So what would I get for the parent acid there?
H2C2O1.
Exactly. How about the last one? I'm going to write this as C2H3O2. So this is going to be acetic acid, so HC2H3O2. Okay, could you all do that if I had you do that on a test? All right, and then let's write the parent base. If you're going to write the parent base, you're going to add a hydroxide ion to the cation in the salt. So here, my cation is potassium, so I would get
KOH.
KOH. How about the next one? The ammonium ion,
NH4OH.
NH4OH. And then I have, this is, since we had a -2 charge on this ion, this is a +2, this Cu. So I would get
CuOH2.
CuOH2. And then this last one is sodium, would give me
NaOH.
NaOH. Easy enough? Okay, let's talk about the second definition of acids and bases, which is broader than the original one, and it's called the Bronsted-Lowry definition of acids and bases. So the Bronsted-Lowry acid definition says that anything that donates a hydrogen ion is going to be an acid. And anything that accepts a hydrogen ion is going to be a base. A lot of times they're going to use hydrogen ions and protons interchangeably. So you'll see that in the reading or some other online resource if you're using it. I'm going to teach you how to predict what is an acid and a base according to Bronsted-Lowry. Let's use this example here. So see how I have an HCl here on the reactant side? I'm going to partner up this HCl with Cl-1 on the product side. Read this from left to right, okay? As I go from left to right, am I accepting a hydrogen or am I losing a hydrogen? Right, so if I'm going to lose a hydrogen as I go from left to right, that means I'm donating it. So that means this substance here on the reactant side is my acid. Okay? Now, if I partner up H2O with H3O plus on the product side, read it from left to right, am I gaining a hydrogen or am I donating a hydrogen?
Gaining.
Right, we're going to gain a hydrogen. So if I'm gaining or accepting a hydrogen, then that means this reactant is a base. Easy enough? Okay. Something we need to talk about is this hydronium ion here. Let's talk about that in a little more detail. Let's do that on the next page. Hydrogen ions are so reactive that you will never see them in solution by themselves. They will immediately combine with water. And they will form a hydronium ion, which is H3O plus 1. I would expect you to know what the hydronium ion is and how it is formed. Okay? All right, I'm going to show you one more example before we do some practice problems. Let's take a look here. I have NH3 here, and NH3 is partnered up with NH4 on the product side. Okay. As I read this from left to right, am I gaining or losing a hydrogen?
Gaining.
Okay, so I'm gaining a hydrogen. if I'm gaining a hydrogen, according to Bronsted-Lowry, that reactant is a base, okay? Whatever you label that reactant, its partner on the other side will be the opposite. So if this is a base, its partner on the other side would be an acid. Oftentimes, you will see them refer to this as the conjugate acid. It just depends on the textbook, the teacher, the online resource you're using, but that's generally what you will see, okay? If I partner up H2O with OH negative 1 on the product side, as I read this from left to right, am I gaining or losing a hydrogen? Losing. So if I'm losing a hydrogen, this reactant is a acid. Because according to Bronsted-Lowry, acids get rid of hydrogen ions or donate them. So if this is an acid, its partner on the other side is a base. We call this the conjugate base as well, okay? Now the substances that I partnered up, like NH3 and NH4 plus 1, or H2O and OH minus 1, these are called conjugate acid base pairs. Conjugate acid base pairs differ by one hydrogen only. Everything else would be the same. Okay, so when I remove a hydrogen, my charge is going to change. It will decrease by 1, and when I add a hydrogen, my charge will increase by 1. Okay, so NH3 and NH4 plus 1 are a conjugate acid base pair, and H2O and OH negative 1 are an example of another conjugate acid base pair. Okay, we ready for some practice?
Sure.
Let's take a look on the next page. Here. For the following equilibria, label the acids and bases for the forward and reverse reactions. I'll do A with you, and then I'll let you do B on your own. HiO3 is going to get partnered up with IO3 negative 1 on the product side. And we're going to read this going from left to right. Am I gaining or losing a hydrogen?
Losing.
Okay, so if I'm losing a hydrogen, according to Bronsted-Lowry, that means I am a acid. So the reactant would be an acid, which means its partner on the other side would be
Base.
a base. Okay? Then I'm going to partner up NO2 negative 1 with HNO2, and I'm reading it from left to right, gaining or losing a hydrogen. Gaining. If I gain a hydrogen, according to Bronsted-Lowry, that reactant is
Base.
a base, which means its partner on the other side is
Acid.
an acid. Now I'm going to show you one more thing. If HiO3 is an acid and NO2 negative 1 is a base, that means HiO3 is actually giving a hydrogen ion to NO2 negative 1. That's if I'm reading this from left to right. Because you'll see that HiO3 is actually losing this hydrogen ion over here, and then NO2 negative 1 now has a hydrogen ion, okay? If I'm going in the reverse direction, then this HNO2, being the acid, is giving a hydrogen ion to IO3 negative 1, okay? Can you do B? Okay. Okay, did you get something like that? Any questions for me on those? You can do this without me? Okay, let's go to number 2. Here we're going to be writing some conjugate acid base pairs, and if we're going to write the conjugate acid of something, we're going to add a hydrogen ion, and your charge will increase by 1. Okay. If I'm writing the conjugate base of something, I'm going to remove a hydrogen ion, and the charge is going to decrease by 1. Okay, I will do the first one with you. If I'm starting out with H2O2 and I want to write its conjugate base, I need to remove a hydrogen ion. So that means this will become HO2. But if this didn't have a charge to begin with, and I removed a hydrogen ion, my charge now goes down by 1. So I go from 0 to a -1. Understand? You want me to go the other way with you? So if I have H2BO3 -1 here, and I'm going to write the conjugate acid, I need to add a hydrogen, which would make it H3BO3, and my charge increases by 1. So if this is a -1, now this has no charge. Okay, what would HCOOH be? Remove this hydrogen and tell me what it would be.
HC2O.
Oh, you can just write OO. And then what am I missing? A -1 charge. And then if I'm going the other direction here, go ahead and just add the hydrogen onto the end there. So C6H5O7H, and then what would your charge be?
-2.
-2, because you were at a -3 over here. Again, can you all do that without me? Okay. Yes.
Why don't we add the hydrogen to the front? Why are we adding it to the end?
I was just adding it next to the oxygen.
Okay.
That's just more aesthetically appealing
Okay.
to me. Okay. Let's take a look at number 3. All right. Here they didn't give you the products, so we're going to predict the products. So if I've got HNO2, which is an acid, and I'm combining it with NH3, which is a base, HNO2 would be partnered up with something that was a base on the product side. So what would the conjugate base be of HNO2?
NO2.
NO2 what? -1. Okay. And then NH3 will be partnered up with something that's an acid. NH4 plus 1. Good job. If I want to identify a conjugate acid base pair, wouldn't HNO2 and NO2 -1 be a conjugate acid base pair? And NH3 and NH4 plus 1 would be another conjugate acid base pair. Okay? Why don't you try B?
So it's not a double replacement.
No.
It's just
Yeah. It's just we're at equilibria. They wanted us to have conjugate acid base pairs. It's just in the directions. I just didn't formally read it to you. Yeah. All right, did you get that? You have any questions for me?
Would it be HCl minus 2?
You've got to add a hydrogen ion, and that means the charge is going to come up one.
Oh, okay.
Yeah. Okay. Okay, last topic. Some substances can act as an acid or a base depending upon what they are reacting with. Water is the most common example of a substance that can act as an acid or a base. It is called amphiprotic. So anything that has the ability to act as an acid or a base, depending upon what you've combined it with, is amphiprotic. That's water, okay? So here is water acting as an acid. As you read it from left to right, it is losing a hydrogen ion here. In this example, here is water acting as a base. It is gaining a hydrogen ion in this example, okay? So I would definitely know that water is amphiprotic, and there are uncharged species, so things that don't have a charge on them tend to not be amphiprotic. What you should do is probably pay attention to substances that have negative charges on them. So anions, generally speaking, are going to be substances that can accept a proton or a hydrogen ion and donate one. So they've given you some examples of amphiprotic anions. This is the bicarbonate ion. This is HC2O4 -1, and this is H2PO4 -1. So what I want to do is take a look at the quick check. I'm going to give you two different reactions where HCO3 acts as an acid and a base, and then we will circle the substances that are amphiprotic in the third question. So for question number 1, they want us to show the reaction between HCO3 -1 and CN -1, and they want HCO3 -1 to act as an acid. Well, that means its partner on the other side will have to be a base. So I'm going to have to remove that hydrogen ion and make it CO3 -2. If HCO3 -1 is acting as an acid, CN -1 has to be a base, and I'm going to partner it up with an acid on the product side, which means it's going to accept a hydrogen ion. So here is an example of HCO3 -1 acting as an acid because it is donating a hydrogen ion to another substance, okay? Okay, now, if I write an equation for that same ion acting as a base, that means this substance is going to have an acid on the product side as its partner, so I have to accept a hydrogen ion, which would make it H2CO3. And if this is acting as a base here, that means water is an acid, and I would have to partner it with a base on the product side, so I have to remove a hydrogen ion from it. Okay? So remember, amphiprotic substances tend to be anions or water. Okay? So if I'm looking at number 3 and it says circle amphiprotic substances in the following list, well, this right here is acetic acid. It has a hydrogen ion that it could donate, but it can't accept something, and this is not an anion. So this is out. Okay? B, H2PO4 -1, it's an anion. So it could either accept and make it H3PO4, or it could lose one and make it HPO4 -2. So this is an example of an amphiprotic substance. Okay? C is an anion, but does C have a hydrogen ion to donate?
No.
No, so C is out. D is neutral, so it's probably out. E has a -1 charge. So let's consider it. I could add a hydrogen ion to make it H2C2O4, or I could remove this hydrogen ion to make it C2O4 -2. So that's an option. Does this make sense?
Yeah.
Okay.